All right, and we are live. All right, welcome back. Let me share my screen for you guys. We'll share the screen. All right, so as you know, this is part 3 of 5 parts of this series on heat pumps. Specifically, we're doing this with Massachusetts Energy Efficiency Partnership, which most of you guys are affiliated with in one way or the other. So we are on the 3rd module. Next Monday, the 25th in the afternoon is the 4th module. And then next Friday, the 29th in the morning is the 5th and final module. So we've covered some heat pump basics thus far, and we've covered rooftop units and commercial split systems in module 2. If you're watching this in the recorded version and this is the first time you're seeing it, you should probably stop and you should probably go back and watch at least module 1, if not module 1 and 2, to get all caught up. For those of you that are live, you are probably in the right spot. Before we begin this week's topic, there were a couple questions already typed in by Gary. Actually, it's one continuing question. He asked if I've looked at the switchover point from electric heat pump to gas burner for the Chicago market, which is fairly close to where I live. He wants to know what outdoor temperature does it make sense with gas being so cheap over here. Gas is usually pretty cheap where I live. Not always, but it usually is. The changeover point, as we looked at last week, is specifically based on your cost of utilities, gas and electric, right, and how they relate to each other, and how efficient your gas system is and how efficient your cooling system is. These are my utility bills because I'm a total nerd and I track this stuff for fun, I guess. But like, for example, right now for the year, I'm averaging a little over $1 for my gas. Last year it was $1.31, 94 cents, 70 cents, 67 cents. So historically, it's been pretty cheap. I'm showing you a screen you can't see. Okay, let me pull my spreadsheet over here. It's been pretty cheap, 70 some cents, 67, 70. And as you might be able to see from what I do with my bills, to make everything fair-ish for gas and electric whenever I track it. And I do this for non-heat pump things also. But I average out the whole bill. So like for my bill for the month, like right now, gas is obviously barely used for me in September because it's just water heating basically. But I put in how many therms did I use? How much did I pay for my total bill? And then I'll divide it out. So yeah, it's showing that I paid $2 a therm for this particular month because right now it's basically all account fees, right? And then, which are fixed, and then my usage fees and taxes on the usage. Whereas if it's like the winter time, right, then it averages out to a much lower amount. And I look at it for the whole year. I do the same thing for electric, take all my kilowatt hours, divide them with my entire dollar amount on my bill, and then I look at what I end up paying. For you guys that have higher electric in Boston area and you're seeing my bill on the screen, I apologize. I feel it's really high here, but you guys are much worse. I think you guys are over 20 cents now. So anyway, guys, I do that. And the reason I do it that way is because if I ask someone how much they pay for electric, like, oh, dude, I got this great deal. I'm paying like 6.5 cents or whatever on this contract with whatever. I'm like, yeah, that's just your energy. Like, what about your distribution charges? What about your taxes? What about your environmental fees? What about your energy efficiency program fee? Like all that stuff. I'm like, I don't know. Right. And then the same thing happens on the gas side. So I do it this way. It just kind of averages out. And I feel it's kind of more fair that way. In any case, back to your question. Right now I'm at $1. I was at $1.31 last year. And my electric was much lower last year. I was at 14 cents, 15 cents. Last year, 13. Now I'm back up to 16. So last year was a prime heat pump year. And it hasn't been that way where I live for a long time. With 13 cents electric and $1.30 gas, I'm just telling people, yeah, your balance point is much different than it was previously. We need to change that. And it paid back last year. It was a good idea to run your heat pump, not your gas. And it hasn't been that way since 2008 was the last time my gas electric relationship was such that my gas was higher and my electric was lower and you should run a heat pump. Other than that, where I live, you really shouldn't run a heat pump. The balance points end up being like in the high 50s, high 40s, low 50s, depending on the models of equipment you have for degrees outside. So it doesn't usually make a ton of sense to run a heat pump when you have cheap gas. Last year, it made a ton of sense for everybody in my area to run their heat pump as much as they could. Now we're back to more of a middle point. Electric went back up, gas went back down some. So now we're kind of at a point where the balance points are usually Right now, for most people's houses, when I do it, it's in the mid 40s, 45. I did one yesterday over in Michigan. I was at someone's house and I ended up sending it for 45. I think the balance point was like, I forget what it was exactly, but it was like 43 point something. So I put it at 45. I like whole numbers. All right. In that regard, and it does tie into our topic today, the first system that we're going to be looking at is residential style split systems. And quite honestly, today, topics 1, 2, and 3 are going to go really, really fast. Like we're going to knock them out in 10 minutes. And then we're going to spend the rest of our time on variable refrigerant flow. Mainly because topic 1 is the same thing we did with rooftop units. It's just smaller systems, which means there's some differences, but the fundamentals are the same. And then PTACs and mini splits are pretty easy too. So residential style systems being put into commercial buildings. Why do people do this? They do it for usually 2 reasons. 3 reasons. 1, first cost. If they can get some residential things less expensively than commercial things, they might do that. 2, they may do it because of space reasons. Maybe they got a really pitched roof and they can't put rooftop units on there very easily. So they have to build these platforms for them. And at some point they're like, nah, you know what? Let's just dedicate this closet to a furnace. We'll throw a condensing unit outside on the front area of the little office building and we'll move on, right? And then the third time is, and this happens a lot, like, I don't know about if it happens by you guys, but by me in Wisconsin, this seems to be like the norm. They want to do high efficiency gas heating. They don't want 80% efficient heating. And the best rooftop you're going to get is typically like 82% efficient-ish. Condensing rooftops are not much of a thing, like we mentioned last week. And if they were, you wouldn't use them in Wisconsin or Boston or Chicago because the condensate would freeze on the roof. So they want to get high efficiency. So they put in small residential style split systems where they can put 95% plus furnaces in with an AC. And then they can get high efficiency gas heating that way without going over to hydronic boilers or anything like that. So we do see a decent amount of residential systems in commercial buildings. I don't remember the exact statistics. I think rooftops are like 54% of the cooling market, but I think residential split systems, commercial cooling market, residential split systems are still like in the high 20s, low 30% of the market. So it's a lot of systems that are like this. Every time someone puts up a little shop building or whatever, it has a little office on the front of their warehouse or whatever, it probably has something like this. So everything's going to work the same as we talked about in modules 1 and 2. You have an outdoor coil, an indoor coil, reversing valve, and the condensing, and all of that stays the same. When you're doing these upgrades, let's put one up on the screen here. All right, hopefully you can see that. Michael's asking if we should be looking at my calendar. No, actually, that's not my calendar. That's the utility training program calendar. I don't think there's anything else coming up next month. Oh, there is. So, hey, while we're on there, we'll make a little plug. October 11th, there's a process and efficiency training. And when you click on that, it gives you the details of all of that stuff, right? And how you register and who's training it and all that. So there is some stuff coming up next month. Right now for September, you're stuck with me though. So I apologize for that calendar being up there right now, but we'll make it like it was supposed to be there. All right, so these residential systems that I was mentioning, get my laser pointer. All right, so we have an outdoor coil. That's this guy right here. Indoor coil. He's right there. He's going to sit above our furnace, or it could be built into a residential air handler system. We have a compressor sitting outside. We have an expansion device sitting inside at the coil, and then we have our reversing valve. Once again, the reversing valve is really the only moving part that is different than a standard air conditioning system. So anywhere where someone has a residential split system like this, right, in any of their buildings, they can automatically change it over to a heat pump. It would not be a problem at all. It's very easy to do a heat pump anywhere that a AC split system used to be. It's not as easy on a rooftop as we mentioned last week, because a rooftop unit, you're going to have a hard time finding a rooftop unit that has a heat pump and gas heat in it. So when you have a rooftop, you're probably going to have to convert to all electric. But when you have a split system, you could do a hybrid system or a dual fuel system, as some of us call it. The reversing valve only moving component. So we're making these retrofits from cooling only small split systems to heat pump versions of them. If you're going to go to from a gas furnace and AC to a gas furnace and heat pump, or it could be oil furnace and AC, oil furnace and heat pump, although I don't think a lot of commercial buildings have oil furnaces at this point, but maybe some of them do, or propane. Right? If you're gonna do one of those type of things, The only thing you really have to do differently is the thermostat wiring. The electrical wiring should be fine in almost every application because the AC unit outside is probably needing the same size gauge of wire and the same size circuit breaker as the heat pump you're going to put in is. In fact, the heat pump might be even a little bit less just because it's way more efficient than the old AC that you took out. Once in a while, you could have a heat pump model that needs a larger wire gauge than the AC would. You just got to look at those kind of things. But like 99% of the time, all of your existing high voltage wiring can stay. The thermostat wiring is where you have to make the change. And I'm going to go back to last week, just for anybody who wasn't on. When you have your thermostat wiring, when you have an AC system, you have typically 1, 2, 3, 4, 5 wires. Up top here is the thermostat. 5 wires from the thermostat down to the furnace or the air handler. When you go to a heat pump, you have 1, 2, 3, 4, 5, 6 wires. You need 1 extra wire because of the reversing valve. So if you went from single stage AC to single stage heat pump, from the thermostat to the fan coil or air handler or furnace, you need 1 more wire than you used to have. And maybe you got a spare wire in the wall, maybe you don't. And then from the indoor equipment, meaning the furnace, air handler, or fan coil, to the outdoor equipment, meaning AC or heat pump, an AC would be 2 wires. A heat pump would typically be 5 wires you need going outside. So typically you almost always have to pull new wire for the outdoor unit to the indoor unit. And sometimes you have to do it from the thermostat to the indoor unit. Now the dotted lines, as we mentioned last time, would mean if you have additional stages. So you're not going to single stage, you're going to multi-stage equipment. You might need even more wires there. If you don't want to pull the wires, as we talked about last week, there are these fast stack kits you can get where you can reuse the existing quantity of wires in the wall and make them into communicating wires and do it that way. So I'm not going to beat that horse to death because we talked about that in the last module in detail. All right. So thermostat wiring almost always needs to be dealt with, and sometimes electrical wiring, high voltage wiring. Now, if you're going to go from a gas system, or I should say a fossil fuel system, we'll make it generic right now, from a fossil fuel system to all electric, right? That's part of your mission, that's your charter in life, because you're trying to reduce emissions or because you bought all these solar panels or whatever the reason is, then you are going to need electrical wiring upgrades because your indoor equipment, furnace in this example, only has a 110 volt, 15 amp circuit or whatever going to it just to power up the fan and the circuit board and those kind of things, not a heater. When you put an electric heater in there to complement your outdoor heat pump, put an electric heater on the inside, you're going to need higher voltage, not 120. You're probably going to need, depending on the heater you buy, 230 volts would be the most common thing you would buy. And then you're going to need a larger circuit breaker because it's higher amperage as well. So you will need electrical upgrades if you plan on going all electric. So that's one of the reasons why I don't usually encourage people to go all electric. There's nothing wrong with it. But there are 3 things that make me usually say, don't go all electric, dude. Go to a hybrid dual fuel system. So we'll cover those 3 things after you see this question here. Anne asks, what about wireless thermostats? You can use a wireless thermostat. The problem with the vast majority of wireless thermostats is that they are wireless from the thermostat down to the indoor equipment, and they still need wires from the indoor to the outdoor. And that's where you have the biggest quantity of wire need. So you could do that. From indoor to outdoor, there's all kinds of tricks. We have like a Ventstar Add-A-Wire kit, a Honeywell Common Maker, Ecobee PK kit, this Fast Stack kit. There's other Fast Stack kits even. There's lots of ways to get an extra wire from this stat to the indoor equipment. There are not a lot of ways to get extra wires from the indoor to the outdoor equipment. And the only wireless product I know that used to have a wireless module for the outdoor equipment was made by a Ventstar T1100 RF model. Not that anyone cares about that. I don't know why I said that. That is no longer manufactured. So I'm not aware of anyone that has a thermostat that can wirelessly talk to an indoor unit and wirelessly talk to an outdoor unit. It may exist, and if someone knows one, feel free to chime in with it. Let me clear these questions off so I don't see them popping up again. Okay, let's go back to where we were. All right, so I was saying there are a couple reasons, 3 reasons typically why I usually encourage dual fuel when people have an existing furnace in their building and they're going to be changing over to heat pumps. Why I would encourage, or residentially too, why I would encourage dual fuel. 1, I don't have to run new high voltage wiring to the indoor equipment, so I save that discussion there. 2, the economics of it usually balance out in favor of running a combination, like run the heat pump when it's these temperatures outside, run the gas furnace when it's these temperatures outside. That usually is the lowest operating cost point for the building owner and occupants. And then the third reason is when you switch to all electric, you may not actually be helping the environment with reduced carbons. You may actually have more carbon output depending on where your power is specifically coming from. Hey, if you're getting it all from solar and wind, I got you, right? I'm totally with you. But if your power is coming from a gas peaker plant or it's coming from coal or whatever in your state, switching to all electric in your building didn't really do anything. Now, maybe it helps for the future, right? And there's benefits to doing that, but dual fuel would help for the future too. And it's a nice compromise in between. So when I say dual fuel, and some manufacturers call this a hybrid system. So I have on the right, indoor equipment and outdoor equipment. Indoor is my furnace, outdoor is my heat pump. In this case, we're showing inverter-driven mini-split heat pumps, but it could be regular heat pumps, could be single stage. This would still apply to all of those kinds of systems. So what's actually happening is my outdoor equipment, heat pump in this case, has refrigerant lines going to the coil above my furnace, just like my air conditioner did. I have supply duct leaving. I have return duct coming in. I have a gas line coming in like my furnace had. I have a flue going out like my furnace had. It's identical to everything that I had in my furnace. I literally just throw my AC away and I put a heat pump there, and then I change my thermostat wiring to accommodate this. Not every thermostat can do this, by the way. You will need to have a thermostat that is dual fuel capable. All dual fuel capable thermostats have an outdoor air temperature sensing mechanism. It's either a hardwired sensor that installs on the building and wires back to the stat, or some manufacturers like Ecobee, for example, get the outdoor air temperature off an internet broadcast. But the stat has to have outdoor air temperature access, and the stat has to be specifically labeled as dual fuel. I don't know why I'm putting that in quotes. It's a real thing. It has to be labeled as dual fuel, and then it'll be able to handle this. You'll set it up as a dual fuel. You'll tell it you have a heat pump and a gas furnace combo. You'll tell it the temperature you want to switch between the two. And that's it. Outdoor temperature, you switch between the two, and then that'll be it. You got to do the math to figure out what that temperature is, but that's how that would in fact work. All right, so some things that are going on. Utilities like heat pumps, obviously, for two reasons. One, and you guys are all, you're not my normal audience. I don't normally talk to utilities. I talk to HVAC guys, so this is like preaching to the choir probably. But one, they probably have specific targets where they're supposed to be reducing their kWh, right? So taking things off of all electric and going to heat pumps helps. And they probably get credits from reducing gas as well. At least in my state, the utility gets recognized by the state. If they reduce total energy, it doesn't matter if it came from gas or electric or whatever. So they like it for that reason. But the other thing is, as you guys know, the peak usage for almost all power plants, at least in the northern half of the country, is going to be in the summertime, right? July, August, that's the peak usage. Every building's running their AC, every homeowner's running their AC, right? And all the baseline stuff didn't change. Water heating, lighting, computers, all that stuff. So the grid, the network of wires throughout the country, state, area, region is all based, and the wires are all sized based on some certain amount of amp flow through them. And that's based on these worst case summer days, plus, some buffering capacity, hopefully, right? In the wintertime, the electrical grid is using much less energy, right? Because people are not running their air conditioners, and instead they're running their fossil fuel appliances to heat, and they're only running a motor to turn a fan on their heater. So the grid usage is much lower in the wintertime. So the utilities don't want you to use a bunch of extra energy in the summer, because then they got to make these giant upgrades to the grid to handle all this stuff, right? If everyone all of a sudden had an electric car tomorrow charging it at home, we wouldn't be able to do that, right? Over time, we can grow it that way, but you can't just do it tomorrow. But if all of a sudden everybody wanted to charge an electric car in the winter, most places could handle that. Not every place, but most places could, because we have that extra capacity because ACs are not running. So more electrical usage in the winter is extra revenue for the utility without extra cost to grid improvements. All right, so hopefully everyone agrees with that. And if I'm totally off base and you guys are like, that's not how we think over here, that's fine. Just unmute yourself and tell me that. But that's kind of the overall mentality, at least from my utilities. So as we're reducing usage of stuff, like we're reducing gas usage at our building, that means we're using more electric typically. Now we have higher efficiencies on things, so we're saving some stuff there as we just improve things over time. But typically, as natural gas usage at buildings go down because we're electrifying them, then electric gas usage at the power plants goes up, right? So like where I live, it's all nuclear. We got all these nuclear plants running, and that's the baseline load. And then as more needs happen on a given day, they bring on additional plants, and those plants are almost always natural gas fired because natural gas fired plants come online very quickly, relatively speaking. So I'm back to using fossil fuels. But instead of burning the fossil fuel at my building at 95% efficient in my boiler or furnace, now I'm burning the fossil fuel at the power plant, sending it over the transmission lines, and there's no way I'm getting 95% of those original therms, right? So it's not very efficient to do it that way. So it's not the best way to go in terms of total energy usage, unless you can upgrade your electrical grid power providers, right? So you're providing wind and solar and things like that. The other side of that is on the equipment side, right? And I'll leave you guys to figure out how to make the power plants replaced with more efficient or more green sources, if you will. On the left here, we're showing BTU capacity based on outdoor air temperature. And on the right, it's efficiency based on outdoor air temperature. And I don't know if you guys can read it or not, so I'll just tell you. Orange in this case is the load of the building. How many BTUs does the building need? And for this case, it was a really small space. The black line was a traditional air source heat pump, how efficient it was, or excuse me, how many BTUs it can make. And as it gets colder, it makes them less and less. Red was a smaller, that was a 3-ton traditional black in black. And then red was a smaller 2-ton cold climate, and gray was a smaller, different model of 2-ton cold climate. So both of these cold climate ones are less BTU ability at their design point for cooling than this one up here in black was, right? But as you could expect, this one here, he's dropping his BTU capacity like we showed 2 weeks ago or 2 modules ago as the outdoor air temperature drops until we get to this point right here, and it can't handle it anymore. This case, instead of putting in a new 3-ton cold climate, it was downsized to a 2-ton. Didn't need 3 tons, seldom actually need what is already there. And in this case, these guys are being modulated, and they could be quote unquote oversped to keep up with the capacity until they finally can't be oversped anymore. And then they tap out and it becomes a flat line going this direction here. But as you can see at colder temperatures, they have more BTU ability than older traditional heat pumps had. You're like, but Ryan, I need more BTUs over here. Okay, fine. Don't put a 2-ton in, put a 3-ton in, and you'll have a curve that's very similar to this guy, and it'll end up over there, right? The efficiency side of the equation, same 3 heat pumps, by the way, same 3 models. This is outdoor temperature on the bottom. This is coefficient of performance. Coefficient of performance of 1.0 right here, 100% efficient. This is where your electric heater would be. So if it drops below where my red dot is, that would be bad. And by bad, I mean that it would be less efficient than if I just ran a straight electric resistance heat. If it drops below that line. So in these guys' case, as you can see, the traditional heat pump, the black one, is obviously not very efficient. It's double the efficiency of electric heat, right? But it's kind of is what it is. Whereas the cold climate ones, which are typically inverter driven and stuff like that, they are more efficient and all the time, but specifically more efficient when I'm 25, 30, 35, 40 degrees. They have a pretty good efficiency because they're not being oversped. They're being ramped down because they're inverter driven at that point. And as outside air temperature drops, so does their efficiency. And they end up just a little bit better than these regular traditional ones. Although I can get more BTUs, but not necessarily a ginormous leap in efficiency. I threw a couple more in there just so you'd have them. We're not going to go through all of them because it's basically telling you the same story. These are all COPs in this case, all 3 of them. So it's the same kind of information we had over here. But it doesn't matter whose study you look at. These are different studies listed on the bottom of them. It's always going to be the same story, right? As outdoor temperature drops, the efficiency rating also declines. So in terms of our buildings, in this example here in dark blue on the bottom, we have systems that have gas furnaces and tankless water heaters, right? And this is how much, let me get this thing out of my way. This is how much energy consumption is happening with those guys specifically. The, what is that color? Gold, we'll call it, is if I converted to an all electric system. So I got rid of my gas furnace and I replaced it with a heat pump with electric resistance heat backup. And I replaced my water heater with a heat pump water heater, right? Then I have these orange lines here. So yeah, in the summertime, everything's pretty similar to what I'm doing now, right? But look at some of these peaks that happen in the colder months, right? When I need a lot of heat, I get these ginormous peaks in my consumption here. If everybody starts putting in all electric heat pumps in their buildings and homes, the utility now has to start dealing with all these giant peaks just like they have to deal with them in the summer now, but it's going to be even worse because, especially residentially, homes need way more BTUs, at least where you and I live, need way more BTUs and hence more kilowatts in the heating season than they do in the cooling season. Commercial buildings, small commercial buildings, that would also be true. If you get to really large commercial buildings, then it's different. We have cooling dominant buildings in that case. Really large meaning like high-rise commercial buildings. This one that's circled here in the light blue, this is a gas furnace with electric heat pumps. And also, it doesn't say here, but also electric heat pump water heater, right? So hybrid systems. And you can see how things are more even, if you will. Yes, it is using more energy than if I had the gas system. That's because right now our utility grid, this is source energy, our utility grid as a whole in most places is not getting its power from awesome places. It's getting it from a combination of things, but also fossil fuels. So my consumption situation for these guys is not as good as if I just kept my old gas and AC system, but it's way better for the utility than if everyone goes all electric. I think that dual fuel is the compromise that we all need for the next 20 years. If our goal is to eventually be, 2050 or whatever your goal is to be all electric and have the power generation that is in a sustainable way, I think dual fuel is the way you get there in the middle. Kind of like I feel the same way about cars, by the way. I drive a hybrid truck. And 10 years ago, I bought a hybrid Prius, right? A regular hybrid, not plug-in. And it's a nice compromise. My next vehicle will probably be a plug-in hybrid where I'm then using grid and gas and whatever combination works best for me at that moment. And then, 15 years from now, my next car will probably be all electric. Where some of my coworkers have all electric now, right? And sometimes it's good for them, sometimes it's not. It just depends on their driving pattern at that time and what their costs are of utilities and stuff. I like this one a lot, and I use this one with all the HVAC guys when I'm trying to convince them to do dual fuel systems. This is 3 examples at 0, 20, and 40 degrees outdoor air temperature. And this is emission rates, right? So basically we're trying to figure out, how much pollution we're putting into the air, greenhouse gas emissions, not pollution, greenhouse gas emissions. So either greenhouse gas emissions, as you probably all are well aware, a lot of that comes from combustion process, which is putting carbon into the air. It also comes from refrigerant leak and other kinds of chemicals that people do stuff with. But in this case, it's specifically coming from the combustion process. We have 3 options of systems on here. This light colored one is a cold climate heat pump. And in this case, it has an HSPF, an efficiency of 11. We have a traditional heat pump. And by the way, this cold climate one was inverter driven. Doesn't have to be, but it almost always will be. This conventional one was 9 HSPF, which is actually a pretty good standard heat pump. That would get a utility rebate where I live, and I think it would where you as well. So it's a pretty good non-cold climate heat pump, meaning it's not optimized for cold weather, probably not inverter driven. And then I have a gas furnace. So when it's 40 degrees outside, this is how much emissions my gas furnace has. When it's 20, it's putting out more. And obviously when it's 0, it's putting out a lot more because I'm running it a lot more, right? My standard heat pump, I have this much emissions. I increase it as it gets colder and colder. And then the same thing with the cold climate. They all increase as it gets colder outside. But if you look what happens is the furnace doesn't increase at the pace that the heat pumps increase at. So if you have a standard heat pump, once I get down to 20 degrees, it's better to run the furnace from a total emission standpoint, national average. Every utility is a little different, but it's better to run the gas furnace than it is the standard heat pump. But if I had a cold climate inverter driven one with a high HSPF, it'd probably be better to still run the heat pump. But then on it down to 0, it's lower emissions to run the furnace, right? So if your goal, like say, or your client's goal is, hey, we want to reduce our carbon emissions, yada, yada, yada. We want to go all electric because of that. It should be like one of these timeout things. Like, is reducing your carbon emissions the only thing? Because if it is, a dual fuel system is probably the way to go. If you only care about first cost, dual system, a regular AC is the way to go. If you only care about energy consumption, dual fuel usually wins. And if you care about carbon emissions, dual fuel usually wins. The only time all electric wins is if you have your own electrical generation from a renewable system available to you, or you're buying a bunch of, SRECs or something like that, where you're paying for someone else's power plant to generate solar power or wind or whatever. Other than those scenarios where you're generating your own power from renewable, or you're buying renewable power from someone, other than those 2 scenarios, there's not any reason why you would go all electric. if you have some kind of greater company goal, you're Coca-Cola and you're like, hey, listen, we're going to be, totally, we're going to reduce all of our carbon emissions by 2030. We need to go all electric. Time out. All electric may not be the way to reduce your carbon emissions. Dual fuel might be the best way. We have any comments, questions, thoughts, arguments on why you might want to think about dual fuel? Someone writes in, Samishka writes in, rebates are higher for electric heat pumps. Does it still make sense to keep dual fuel hybrid since operating costs can provide some of that savings? All right. So like, for example, we'll actually pull it up here because we'll do one of the, discard the notes. Let's pull this back up from earlier on in module 1 to try to address what you're saying. Where did I put it? Let's use this one. This one will work. All right. So like, for example, Residency, where you guys live, if you go to, a completely all electric system, you can get $10,000 rebate at your house. If you go to a partial upgrade where you still have some fossil fuels, i.e. a dual fuel system or hybrid system, you get $1,250 per ton. Let's say you have a 3-ton system, because that's a pretty common size. So that gives you $4,000. You get a $4,000 rebate instead of a $10,000 rebate, right? So $6,000. In that case, what you could do is do the math to say, well, how many years would I be operating, right, to pay to penalize me enough for that $6,000 gap, right? So depending on your electric rate and your gas rate, obviously, maybe it takes 3 years, and then all of a sudden you're like, dude, I used all that extra $6,000 to pay this much higher electric bill than I've ever had before, and now I'm back to being even again, right? So it'll depend on your rebate, obviously, and your efficiency of your two systems, your fossil fuel and your electric. Now, if you're going to move out of this house in 2 years, dude, I'm doing this one all the way. Get the $10,000 one, right? It's probably a marketable thing to say I have a heat pump, right? I'll get my $10,000, and I don't care about the operating costs after 2 years because I'm not going to live there after 2 years. That'll be somebody else's tab to deal with. Hopefully that sort of kind of answers the question. Let me go back to where we were. Where were we? We were probably close to there. We were probably there. All right. Moving on. Some of you guys were trying to use some of those calculators that I had used last time. And they're specific to specific manufacturers, as I mentioned. I think I sent 3 manufacturers calculators that are all kind of similar. If you're looking for something more generic, I use this chart quite a bit. I do realize looking at it, though, it's probably not going to help you a ton because you guys are now at the point where you're more than 16 cents a kilowatt hour. So it's probably not going to help you a ton. I'll have to try to find a chart that goes even higher, or maybe I can just extrapolate this chart a little further. But let's just say, well, where I live, Illinois and Michigan, as you saw my utility bills, I am right here now. I'm at the end of this chart as well. I need to find a new chart either way, just for my own purposes, right? But if I had this scenario here where I'm paying 16 cents and 85 cents a therm, I would be right here. I guess you could do it without all of your fees and everything included. Like my raw gas cost is 10 cents, or my raw gas electric cost is 10 cents, and my raw gas cost is 70 cents. So I'm over here somewhere, 55-degree changeover point. If I do it like the way I normally do it with all my bill averaged in, you guys saw I was at like 16.5 cents and a little over $1. So I'm over here, same kind of answer. There and there, very similar answers. In both cases, 55 or 60, where I'm at in my office building or in my house, I'm not running the heat pump at all. Because once it's 55 at my house, I'm not even running heat. Heat's off. Like that's a warm day. And my office building's the same way. We usually get down into the upper 40s, lower 50s before we switch from AC to heat. So in those cases, I wouldn't run the heat pump at all. Now, if my electric rate is low and my gas is high, like I don't know if someone wants to type in like what you guys are paying for gas right now, but my guess is you're probably like $1.30, right? And then you're probably, I don't know, what are you, 20? I guess you're gonna be the same boat. You're gonna be 50 degrees also. So for generic models of equipment, heat pumps and gas sources, it probably doesn't make a lot of sense to run the heat pump. Now, if you're paying something more ridiculous, like if you guys are on oil or propane and you're paying, you know, $3-4, now you're way over here on the chart, right? So now it's like, oh yeah, if you got, you know, propane or oil, let's just say propane because it's on this chart, and let's say you have 16 cents electric and your propane's 250, 0 degrees. At 0 degrees and below, you'd run your furnace, right? And then 0 degrees and above, you would run your heat pump. Now, if your heat pump has a thermal balance point of 20 in your application, it's as far as it can get enough BTUs for your building, then obviously you won't change it over at 0. You change it over at 20 because you can't make it down to 0. So for dual fuel systems, you will do the changeover at the higher of the thermal and economic balance points. So let's just look at that one more time. Go back to module 1 real quick. All right, we'll look at this will work. All right, so on this particular situation, we looked at this two modules ago. Let's say I have a 3-ton model. This is a certain model of heat pump. I have a 3-ton, and this is the BTU capacity I can get. This is the load of my building. I follow how much capacity my unit can make, and where it crosses the load of my building, in this case, 27 degrees. At 27 degrees and below, my heat pump can't make enough heat to heat my building for me anymore. So this triangle over here, it can't handle it. It's doing this, but I need that. So below 27 degrees is when my electric resistance supplemental heat would kick on and help the heat pump out. But if I have a dual fuel system, I don't do that. I shut off the heat pump and I turn on the fossil fuel system. So at 27 degrees is when I would switch over from heat pump to fossil fuel. If my electric balance point cost, my economic balance point said, hey, you could do it at 15, okay, that's great, but I don't have enough heat. So I'm gonna have to do it at 27 anyway. But if economically it said to do it at 40, well, at 40, okay, I'll switch it at 40. So whichever one is higher, the thermal balance point, which I'm showing you here, or the economic balance point on a dual fuel system, meaning any heat that's not electric, fossil fuel basically, I will do it at the higher of the thermal and economic balance point. Holy cow, someone said you're paying $4.45 for 40 gallons of propane. Jeez, oh my God. All right, well, you guys pay a lot. If I'm looking at those software tools we were looking at before from an energy standpoint, if you remember this, I put the load information of my building in. I picked some old existing AC they had, and then I had different upgrade options here. And it told us our various paybacks. So I'm gonna ignore that for right now, which is, it's all good info, but right now I want to look at these two numbers, thermal balance point and economic balance point. And once again, this software tool, the specific one, is for small systems like residential type systems. For bigger systems, usually I'll use HAP or something like that to energy model. In any case, thermal balance point for this particular model of heat pump, which is a 16 SEER 9H SPF 2-stage heat pump, thermal balance point was 38. Economic was 22. That means at 38 degrees and below, that model of heat pump cannot make enough heat for this building, and I need to switch over, or in this case, all electric. I need to add on electric heat. Economically, if I get down to negative 22, that's when I get below 1.0 COP on the heat pump, and it would be cheaper to turn the heat pump off and run the all electric. It's probably never getting to negative 22, so I'm probably never even have to think about that. This model of heat pump, which was inverter driven, cold climate type heat pump, thermal balance point 23, meaning below 23, I don't make enough BTUs for this exact heat pump and size in that exact building. And negative 17 is when it'd be cheaper to actually run the other source, which is all electric. Oil and then gas. I'll use the gas one for right now because that's kind of what we were looking at a minute ago. For this gas one, and granted this one was at 16 cents and $1.10 for gas, which was your guys' gas rates a couple years ago, I think, when I made it, and not anymore. Our electric rate a couple years ago, not anymore. But in any case, these are the same pieces of equipment. Thermal balance point, 38 degrees, right? Because it's the same unit, 38 degrees, 23, 38, 29 in this case. Maybe it was different. Oh yeah, because it was a furnace on this one instead of a air handler. So it makes it a little bit different from a evaporator coil standpoint and a pressure drop standpoint. But in any case, if I did this all electric system, 38, negative 22, like we said, I switched to the hybrid system, dual fuel. My thermal break point was 29, meaning that this particular combination of equipment could get me down to 29 degrees on heat pump alone. Economically, it was 60. meaning if it's below 60, it's more expensive to run your heat pump. Don't do it. Run your furnace, dude. Right. And then as we change these numbers, we'll see though this guy change. Right. If I make the electric cheaper, then this breakpoint goes down. If I make the gas more expensive, this breakpoint goes down. Mark types in, have you worked with customers who have also used KW demand to manage changeover on dual fuel systems, i.e. set a limit at some measured whole facility demand number? I have not, and mainly because most people's demand is coming off of their summer bill, right? And then you're paying that for an extra 11 months of penalty. You do have demand charges that are also your monthly demand charge, but usually the big dollar amount one, at least where I live, is the peak that happens in the summer. So shedding KW load in the winter doesn't really do much for me. Now, if the building starts using a lot of heat pumps, right, and it's a heating dominant building, then that math would change. I don't know. You'd have to do it manually. I don't know any, or building automation system. A thermostat wouldn't be able to handle what you want to do there, Mark. A building automation system could, if you set it up to communicate to the utility to send a demand load shed signal. Or you can do it manually, right? If you're a big building, you're a Caterpillar factory or something, and they call you and say, hey, dude, if you can just like shed this much load, we'll give you a check for this. Then I could see you doing it. But for like normal systems with a thermostat, like a rooftop or the small system we're talking about today, nobody's thermostat is going to do demand reduction charge switching dual fuel. I need to find a better way to skip to back to where we were. Okay, so that just gives you an idea there. I'm going to, some of these slides are in there so you guys will have them, but this is just showing you some study data. This one happens to be Michigan, a bunch of retrofits and existing homes in this case. By the way, there's a lot more data for small heat pump studies for homes than there are commercial buildings, because homes have a much larger heating need than commercial buildings do. And so they use a lot of small systems, obviously. So there's a lot of data and studies I can go pull from, whereas commercially there's a much less done with these small systems for studying them. But some of this data is in here for you guys to utilize on your own if you want. This one with those 8 systems there in Michigan. And there's a variety of stuff here, and it's interesting. Like, so it shows you on here if it's single stage, 2-stage, or variable speed inverter driven, what they had configured for various lockout temperatures, and then what they were able to get for operating cost savings for the homeowner, and what they're able to get for energy use reduction at the site, and what they're able to get for emissions. And what you'll find is that there's a large variety of combinations of things that get you the answer. There's no silver bullet that says, hey, dude, you put a variable speed inverter in, you are gold, man. Because I can find a variable speed inverter on here that did a good job, save these people a grand a year, 67% in their energy reduction, right? And then I could find other ones that are less. This one's only, quote unquote, only 41%, which means still really good, right? But I can find different scenarios on here. But those changeover points and combinations of equipment types you have make a difference. And this kind of goes along with that same study. So these all go with that same study. In the interest of getting us back on schedule, I'm going to leave these here. If you have questions on them, and later you can email me and ask me. But these are in here for your use if you want to see the rest of that same study in those sites, and if they just tweak some of the changeover points on what they could do from an efficiency standpoint. All right, PTACs, package terminal air conditioners. This is a one-slide thing. This is the whole thing. This is the whole module. A PTAC, every model of PTAC is the exact same width and height. I say every, 99% of PTACs are the exact same width and height and the same plug that goes in the wall. It is a complete and total commodity. Obviously, it's dominated in the hotel market, but you'll find it in condos and apartments and other stuff like that. You pull a PTAC out, you buy a new one, it slides exactly into that same sleeve, and it plugs exactly in that same spot on the wall, and there's basically no thinking involved. HVAC companies don't even get involved with these at this point. Hotels just buy them directly and typically do their own thing. If one fails at a hotel, they got 100 rooms at the hotel, they have 107 of these PTACs. There's 7 of them sitting downstairs in their maintenance room, ready to swap it out if they need to. With that being said, there is an opportunity to save energy with these by using a packaged terminal heat pump, PTHP. Nobody calls it that. We just call it a heat pump PTAC because there's a vowel in PTAC, so it sounds better. But the PTAC version, guess what? It's the same width and same height, the same electrical plug. You slide the one out, you slide the one in. You don't need to do any electrical upgrades in most cases because the existing PTAC, the AC version, has an electric resistance heater. And when you put the heat pump version in, it's not going to have any bigger of an electric resistance heater. And the heat pump's going to take most of the workload anyway. So it's a pretty easy swap out. It doesn't even matter what size capacity is. A 9,000 or a 12,000 BTU model is the same width and height as each other. They literally all fit in the same box. Most hotel rooms do not need more than 9,000 BTUs anyway. So in any case, the situation here would be if it's apartments or hotels, they would work with that building maintenance staff to, when they buy the ones for inventory that they stick in their shop downstairs, you would buy the heat pump version ones. You'd have them ready to go. That's one strategy in placing. As they fail, you swap a new one out, right? The other strategy is to go through wholesale and just say, hey, we're just going to replace them all. Like, we're going to take this year and we're going to do 10 hotel rooms a week, and we're just going to start swapping them out with PTAC versions. So you can do it that way as well. But it's really easy swap out. Like, there's nothing extra you have to do. Just slide it out, slide it in. It's like a no-brainer. So that's why there's literally only this slide for that. Ductless mini splits, it's a little bit different. So these are obviously not as common as PTACs. You will find these in all kinds of random applications. PTACs is pretty much like hotels, condos, senior citizen homes, and things like that. Ductless mini splits are all over the place. You'll find these in people's houses. You will find these in office buildings. You'll find these in add-on areas. You'll find them in a workshop. They'll throw one in to get a little bit of cooling in there. All kinds of scenarios. In most cases, you probably won't be swapping one out because it's not like a super long established market where we've had all these in for decades. I mean, there are applications like that. But historically in commercial buildings, the only place we used a ductless mini split would have been like a server closet at an office building, right? They got this, whatever, 10 by 12 room that has a bunch of server racks in it. They need some cooling in there. You buy a cooling only AC ductless mini split, and ductless was fine because you don't care about ventilation air because no one's in there. There's no people. It's just a storage area, right, for electrical equipment. So you'd buy this ductless mini split. You throw it in there. It would be one that had low ambient cooling because you could run cooling when it's 0 degrees out, and that would be it. That's what you're going to find mostly in the existing market in commercial buildings. And there's no reason to swap that to a heat pump because that application doesn't need heat. However, when you get a new ductless mini split, it's going to be a heat pump because almost no one makes cooling only versions of these anymore. There are a few, but generally 90+% of the market is heat pump version. So the AC one dies, you put the heat pump one in. You just don't ever put it in heat mode because you don't need heat in that server room. So we're not talking about those applications because those ones obviously don't need any heat. The other applications are going to be where you do have occupant areas. So the common applications for these mostly are add-on places that didn't have cooling before. So maybe you got steam radiators in some kind of loft building, and now you're going to retrofit them and you're going to add some cooling. Instead of just adding cooling, why not add cooling with a heat pump? And you can run the heat pump and take some load off of the steam boiler and only run the steam boiler when it's below X degrees outside, and above X, you run the heat pump, right? And we'll do the same kind of dual fuel economic balance calculation with that steam boiler as we did with that gas furnace, except for now we're doing it for the whole building because the steam boiler is probably feeding lots of spaces, not just one room like we did with the other one. We'll talk more about the steam boiler options and stuff like that when we get into, actually it'll be Friday this week, we'll do that. So the ductless mini splits, they are the exact same components we've talked about all along: indoor coil, outdoor coil, compressor, expansion device. The one thing about the expansion device, TXV in this case, actually two things. One, it's probably an EXV, electronic expansion valve, instead of a thermostatic expansion valve. That means a circuit board is going to drive it instead of an analog temperature probe. And then two, instead of that TXV being at the indoor unit, it's probably going to actually be at the outdoor unit. So on a normal system, the ones we've talked about so far, traditional split air handlers, RTUs, or dual fuel furnaces, these components are inside the building, right? And then these components are outside the building. But now on most mini splits, the EXV is in here. So these components will become the outside components. My drawing's fantastic. There's probably a better way I could have done this, people. Discard. Oh, yes. So now, dang it. Now these components will be outside. This guy switched He switched teams. He's not on the outside now. So what does that mean for you? From an operational standpoint, it doesn't mean anything for you. It works exactly the same way. The fundamentals are the same. The servicing is the same. Installation-wise, it is a little bit different. The two refrigerant lines connecting these guys, because this device is out here, both lines have to be insulated on these ductless mini splits. Not every single manufacturer, but nearly every manufacturer does it that way. So almost every non-mini split, the expansion device is at the indoor unit, and almost every mini split, the expansion device is at the outdoor unit. So that makes a big difference on what I gotta do from an insulation standpoint. So I gotta insulate both lines. So if you're gonna try to reuse existing line sets and you're going from an AC to a heat pump, you probably will have to put a new line set in or go back and somehow get insulation across the old line set, which is really hard because it's anchored to the building in all these different spots. So it's easier just to pull a new line set in most situations. So keep that in mind in the cost scenario that you may have to do that. There's also multi-split systems. So what this is it's one outdoor mini split system that is feeding not just one indoor unit, but 2, 3, 4, 5 indoor units. In this case, each one of them has 2 refrigerant pipes going back to the unit. So there's 1, 2, 3, 4 ports on this guy. This drawing's bad. It should actually show them going to each of these ports. But there's a pair of ports going to each indoor unit. So in this case, it works the same way. The outdoor unit's a heat pump, so it can either be a condenser or an evaporator. The indoor units can either be a condenser, evaporator, coil. Both lines get insulated. The idea here is you can locate different zones. So like maybe I have 4 offices next to each other, and each person wants to have their own individual control. They're all very important people. They can't possibly share a thermostat. You could give them each one of these heads, right? And they can each have their own little handheld control or wall thermostat that they use independent of each other. And this is just showing you different kinds, right? I could have 4 of these cassettes, right? Or I could have 4 of these high walls, right? Or I can mix and match them. It doesn't matter for most manufacturers. So that way individual control can be had in each room. However, this unit can only be in either heating or cooling at any given time. So if this guy wants heat, well, this guy wants cooling, that's not happening. It's going to do one or the other. It can't do both, right? So if that scenario happened, this dude just got to wait. He can go ahead and turn off and just sit there and wait until this guy gets his heating needs taken care of. Then it can shut off and switch over and do this guy for cooling, right? So with that being said, when you're going to do this in a building, this is my crude building right here. And let's say I have those 4 offices I talked about. This would be an okay example. These are all on the north side of the building, except for the little edges over here. So there'd be a little brief moment in time. Right here's west, right? So there'd be a brief moment in time when this guy could want cooling while this guy wants heating. It's not going to happen a lot, but it could happen a little bit. Whereas what I definitely don't want to do is I don't want to divide my building like this. Those 4 be my zones, right? And this guy is going to want, this guy's west, right? He's going to want heating all afternoon. All this area wants it. This guy's north. He has no direct sunlight. This guy has sunlight the whole entire day. And this guy has it in the morning. If you have a situation like this, we have multiple zones. And that's not just a heat pump situation. Any system like this, zone damper system, multi-zone, VAV, we could do it if we have reheat coils. But normally you don't want to mix exposures on the same system if you can avoid it, because different sides of the building need different things. So that would be a problem. But I could put in one of these my drawing is so jacked up now. All 4 of these over here. I could put it in another system with 2, 3, 4 zones over here, put another one over here, another one over here, right? I can accomplish it with multiples of these depending on the size of my building. But I generally don't want to put mix exposures. And you generally don't want to mix interior and exterior either, right? So I got to clear this off. You don't want to mix interior and exterior either, right? Because on a big enough building, I don't know if we said this on module 1 or not. Once I get like, let's say 15 feet from the exterior wall, this is cooling only year round, nonstop, balls out every day, no matter what. I don't put heaters in those spaces. I literally don't put them in. I don't design them in there, right? Because if this guy's sitting here in the middle, the zones next to him, it's 72 degrees here, 72, 72, 72, 72 on the floor above, 72 on the floor below. All 6 sides of that middle box, it's 72. That zone thinks it's sitting in San Diego. It has no idea it's in International Falls, Minnesota or whatever, or the upper coastline of Maine. It doesn't know. It just thinks in San Diego, and it wants cooling all the time because everything around it is neutral or warm. Whereas the perimeter zone, he's sitting here and it's 0 degrees outside. He's like, dude, I need heating, man. I'm like, are you serious right now? It's heating season. So don't mix perimeter and interior on any kind of zoning system, not just ductless mini split heat pumps, but any kind. There are other options to do that with heat reclaim VRF, and we'll talk about that in a couple minutes here. Actually, we're probably at the point of talking about it now. I think that's our next slide, I think. Just a couple examples of mini splits. Just like other heat pumps, when you put these in, you need them to be above the snow line. That's why you're seeing them on all these different kinds of stands and on brackets and stuff like that. You don't want any heat pump to be installed if it's going to operate in your climate or mine. I mean, if you're doing this in Miami, do whatever you want, right? But I don't want it straight on the ground. For one, I need it raised up a little bit because there's going to be a drain on there. A normal air conditioner does not have a drain on it on the outside unit. The indoor unit does. The indoor evaporator coil does, but the outdoor unit doesn't. But a heat pump, remember, the evaporator and condenser switch jobs. So now in the heating mode, my outdoor unit is the evaporator coil, which means condensate's going to form on it, and that's going to drain down. It needs to go somewhere. So I got to raise the heat pump up a few inches in order to have that drain be able to come out the bottom of it and then go away. Additionally, if you're in an area that has snow, which you are, you're going to want to raise it up above the normal snow line, because if I have snow drifting up on the side of it, it's going to pack on the bottom of the heat exchange surface, and that's going to reduce my heat transfer, and it could eventually also freeze up my coil that way, because now new water running off of it lands on that snow, and that becomes ice, right? And then new stacks on top of that. So you have to raise heat pumps up, and you got to raise them up above the snow line. How high? That's always an argument. Even in my office, we do business in Illinois, Indiana, Michigan, Minnesota, Wisconsin, all very similar kind of places, in my opinion. And in the Chicago area, all of our guys want it raised up 18 inches to be above the snow line. But then in Minnesota, they only buy the stands that are 9 inches. And I'm like, dude, I don't understand. Minnesota, you guys get 4 times the amount of snow we get. Why do you guys all have these different rules of thumb? And actually, honestly, it comes back to the fact that the guys in Minnesota are really good at dual fuel. And they're like, dude, when I'm below 40 degrees, I'm not even running the heat pump. So who cares? Like, all right, valid point. All right, VRF, unless we have more questions on that. William says, what would hurt the efficiency of a new mini split? I have a Mitsubishi 3-ton with a distribution box. Would it be 3-phase, possibly wired wrong, possibly too much refrigerant, or too little? All of those things can damage a system. So you wire something wrong. Obviously, if you connect high voltage to where they're supposed to be low voltage or anything like that, you could damage stuff. Running undercharged or overcharged is always a problem as well. Although most of these systems we're talking about are higher end systems, meaning that they do have pressure switches on the refrigerant side. So if your refrigerant pressure is too low, the switch will open and shut the system off. If it's too high, switch will open and shut the system off. Whereas old school, traditional, plain single stage heat pumps typically don't have those switches, because those things are being designed for first cost markets in Georgia, right? So they don't have those extra protection devices unless somebody upgrades to the nice model. So if you have too low or too high of refrigerant, like really too low and really too high, the machine will just shut off and protect itself. But yeah, there's no shortage of things that can go wrong on a mini split, but there's also no shortage of things that can go wrong on VRF, on a furnace, on a chiller. There's all kinds of things that you could inadvertently have going on. Let's do some VRF stuff, because we got another half hour. All right. So let's do an hour worth of VRF in a half an hour. So VRF stands for variable refrigerant flow. One manufacturer calls it VRV, variable refrigerant volume, but everybody else calls it variable refrigerant flow. So generically, VRF is what you hear stated. This is very similar to that mini split we were talking about, a multi-zone mini split, right? It was similar to this scenario where I have multiple indoor units on a single outdoor unit. Same kind of idea here. Although in this particular example, I have 2 outdoor units twinned together. That's possible, sometimes even 3. But basically, conceptually, I have 1 outdoor unit feeding a bunch of indoor units. The differences between this and that multi-split system that we were talking about. This one is actually going to be 1 piping system that goes down the building, either 2 or 3 pipes that go down the building and then splits off to the individual zones. Whereas the other one, everything was piping home run back to the outdoor unit. So that's a different way of installing it here. I can also have more than like 4 or 5 indoor units. Like these other ones, 2-ton, 3-ton, 4-ton. Maybe somebody makes a 5-ton system. That's probably it. Here, we're probably talking usually 6 tons and up, but there are some models that are 3, 4, 5 tons, but usually 6 tons and up. You might have 10, 12, 15 tons of cooling capacity here, feeding all these indoor units, right? The next thing that's going to be different is there's going to be 2 flavors of this, 2-pipe and 3-pipe essentially, meaning that I can do simultaneous heating and cooling or I can't. And then if I got that building with that San Diego thing, right, cooling in the middle, heating on the perimeter, this would come into play for that example. Everything we mentioned about a heat pump is going to be true in this case. Everything. So I'll skip that. Indoor evaporator coil, outdoor reversing valve, all the same kind of components that we had a minute ago. VRF is not new. It's been around for decades, but it didn't start becoming a US thing until the mid 2000s. I think in my office, we did our first system in 2008. Most manufacturers, at least where I'm at, didn't start doing it till around then as well. But I guess probably in the United States, looks like 2000, that's water cooled. Somewhere around here, there's a United States thing. 2003 or something, we had manufacturers bringing it to the United States. One of the nice things about variable refrigerant flow is we vary the amount of refrigerant. So we vary the capacity control. So everything's going to be inverter driven. Well, I shouldn't say everything. Almost everything's inverter driven. And as you know, we have different needs based on the time of year, right? So this is how many hours, I don't know if I showed you something similar to this previously or not, but this is how many hours we run at different points of the year. So if I just look at between 80 and 85 degrees, right? That band of 5-degree outdoor air temperature, that dude, let's just call it 250 hours a year are in those 5-degree bands. Whereas if I look at 60 to 65, way up here, I got 950 hours, right? So the systems that we have, whether it's VRF, heat pump, non-heat pump, whatever, these kind of systems were typically designed for certain outdoor conditions, right? Every cooling system is designed and tested and rated by the manufacturer and AHRI at 95 degrees outdoor air temperature, right? But in Boston, how often are you at 95 degrees? Hardly ever. It's like a little sliver. I can't even barely see it on the line. It's like X amount of hours a year, single digits typically, unless it's a freak year, right? By the way, this data that on this screen is a 30-year rolling data kind of thing. All right, so you're not spending a lot of time there. So I don't really care how efficient somebody's thing is at 95, right? And that was always our EER number for various types of equipment. It's like, okay, great, you're really efficient at 95, great. I don't care. How efficient are you at part load? Well, with old systems where everything was on off, if you were efficient at full load, 95 degrees, you were equally efficient at other loads, right? Like relatively speaking to other equipment. But now with inverter driven technology where I'm speeding up and slowing down compressors, speeding up and slowing down condenser fans, speeding up and slowing down indoor blowers, I can be more efficient at part load. And that's what really matters. As you can see, here's part load cooling, here's part load heating, right? So how efficient are you at all these hours? Because these hours don't matter. I mean, they matter. I got to size my equipment to handle those days, but I don't care if it's super inefficient to heat my building when it's 0 degrees. I don't care. If I'm saving heat energy all the other days of the year, I'm good with that, right? So just kind of keep that in mind. Instead of my crude drawings, I guess I could have just showed that, right? Cooling days, heating days. All right, so VRF systems, we're going to move the energy around the building with refrigerant instead of moving around with ductwork. So generally speaking, no ductwork and not even water, which would be boilers and chillers. This is just to give you an idea, give you an example. This is how much energy I can move through air, 7.7 BTUs of energy for every pound of air. If I go to water systems, I'm averaging 20. And if I go to refrigerant systems, 117. Moving heat around a building with air or cooling around a building with air is the worst way to move energy around a building. There is no worse heat transfer media we use in HVAC than air. Ductwork is our enemy, right? Now, I still need air. I still need ductwork. I need ventilation air coming from the outdoors, right? Don't get me wrong on that. But if I can do stuff, moving energy around the building with other fluids, water, and in our example today, refrigerant, that's going to be significantly more BTUs I can move through a smaller amount of area. If I look at it from that perspective, a 16 by 48-inch duct can carry a certain amount of capacity, 10 tons of cooling. I could do 10 tons of cooling with 2-inch hydronic water lines, or I can do 2 tons of cooling with even smaller than 1-inch refrigerant lines. Right, so I can move a lot of energy through a building without taking up very much space. This is 12 tons of cooling running through a duct system. This is 40 tons of cooling running through refrigerant piping. It takes up way less space. That means this kind of system is really nice for retrofits where you don't already have ductwork. If you don't own ductwork, why are you even looking at putting ductwork in? So especially if you're converting a heating only building to cooling, this becomes a pretty good option here. The two flavors we have on VRF, 2-pipe and 3-pipe. Although some manufacturers do it a little bit differently with a phase change inside a 2-pipe system. But we'll just talk about the basic one for now. A 2-pipe heat pump is like all of the other heat pumps we showed before, including that multi-zone where I had the 1 outdoor unit and the 4 little baby indoor units. It works like that. So in this case, I have 1 outdoor unit and I have 1, 2, 3, 4, 5, 6, 7 indoor units. They can either be in cooling mode in blue, or they can be in heating mode in red. I cannot have one in cooling while one is in heating. I can turn some of them off. Like I can say, you know what? This whole perimeter right here needs heat. All 3 of these guys need heat. But these zones don't need any heat right now. They're on the west side. The sun's hitting them. I could turn these 4 off while running those 2 from heat. But I can't give these 4 cooling while giving those 3 heat. Right? They'll have to wait their turn because the outdoor unit can only do 1 mode at a time. Right? From an installation standpoint, you'll have copper lines running to all these indoor units. What happens on majority of manufacturers is I'll leave the outdoor unit at a fairly large pipe size. And as I get further away, so I don't know what the size is, but let's just say, I'll make up numbers for right now. Let's just say this is 1-inch line right here. And then I'll pull some BTUs off on this tapping to go to this first unit. And that means this is no longer 1-inch line. Now this is a 7/8 inch line going over here, right? And as you get further away, it gets smaller and smaller. So the size of pipe you need will be pretty large if you have a 20, 30, 40 ton unit versus a 6-ton unit. But the piping starts out large and then it just keeps tapping off, kind of like ductwork does. You start off with a big, huge duct, and as you get further down, you pull some zone duct off, and now your remaining duct gets smaller and smaller as you get further down the line. You'll insulate both of these lines because the metering devices are out in the unit, like we said before. You may or may not have thermostats on the wall. Some of the times they'll have the handheld, remote control. Other times they'll have thermostats on the wall. Just depends. And then there'll be communication that goes from the outdoor unit to the indoor unit, and then to all the other units, and typically in a daisy chain fashion. So like a building automation system would have. This particular example is 2-conductor shielded stranded cable. You move that from each unit to each unit. So for starters, that means you cannot mix and match brands. If this is manufacturer A's outdoor unit, these have to be manufacturer A's indoor units, and they have to be the ones that go with that one. They may have different models for other reasons they use in different states or countries or whatever they do. You need the ones that pair to that so they have the ability to talk to each other. If this unit dies, and let's say it's from manufacturer A, you can't go get a manufacturer B one 16 years from now and throw it in. You got to get one from A that communicates with this, right? So whereas like traditional building automation systems, I can have a VAV box, and that VAV box could need to be replaced, and I can go get it from anybody. I take the tightest box out, I put a nailer box in, it's not a problem, right? Because I put my own controller on there. The same controller goes back on there, right? Whereas VRF is not that way. Everybody's matched system. Good news, bad news on that. The good news is it's already optimized to work really well together. Whereas a building automation system, you're relying on the field building programmer to make everything awesome. And that dude may be awesome, or he may suck, and you just don't know until it happens. Whereas this is optimized by design, at the factory level. So that's the good news. The bad news is you can't replace things randomly. You have to be very specific about it. All right, so all these guys, there's an expansion device outside. There are expansion devices inside. It's showing them on the piping here, but they're actually in the box. As those zones need less capacity, they throttle their expansion device, and they can change their indoor fan speeds. Either they'll have a fully variable one, or they'll have like a 3-speed fan or something like that. So in this particular example, we have an 8-ton model outside, and my peak loads for these guys are 3 tons, 3 tons, 2 tons, 2 tons. So you notice right off the bat, I have 10 tons of capacity connected to an 8-ton unit. How the hell is that going to work? We're banking on the fact that all 4 of these zones are not calling for the maximum amount of heating or cooling at the exact same moment in time. So it is very common to put more indoor units than outdoor. Each manufacturer's model has different rules. They'll allow you to add 20%, 30, 40%, right, above whatever this is on here that you can call connected capacity. In this particular moment in time, however, this 3-ton has modulated himself down to 1 ton. He's 1 ton. He's off. He's 1 ton. So 3 tons. So my 8-ton unit is going to modulate itself back down to 3 tons. That unit is probably a 2-compressor system. Each one of them is probably 4 tons. One of them shuts off. The other one modulates from 4 tons down to 3 tons capacity. The other type of VRF system that is common, and this is one that's really cool, is what we call a three-pipe system, or most manufacturers call it that. Some call it a three-pipe, some call it a three-way. You might hear the words heat recovery or heat reclaim. In this scenario, everything looks exactly the same. The difference is, instead of two pipes running down the building and splitting off to the zones, I now have three pipes running down the building. Think of it as the fact that you have a hot pipe and a cold pipe and then a return line. It's not exactly like that, but just think of it that way. You basically have liquid suction and hot gas available to you. So each one of these guys, if you can see, there's a little box added on here. Three pipes come in, two pipes go out. So this box, the zone with the fan and the expansion device, talks to this switching box. And he says, hey, dude, I want cooling. These guys are on cooling over. I want cooling. This guy switches to the cooling pipe. Well, this guy says, I want heating. He has his box switched to the heating pipe. And this guy is able to run both simultaneously. And I'll explain that in a little bit as well. Sometimes you'll have one-to-one relationship. Sometimes you'll have this box switching for all three of these guys because it's just one big room. And the only reason I have three of them is just to get good distribution in this space. So I'm not putting all the cooling in one corner only. But as far as modes go, I'm never going to want him in cooling while he's in heating, so they can share a box. Schematically, everything looks the same as before, except I have three pipes running down the building instead of two. And then I added this switching box over here where three pipes come in, two pipes go out. Everything else is the same as it was a minute ago. That's not the only way to do it, right? The way I just described was this way or this way, right? So I got this piping running down the middle of the building. It branches off. Each one goes to a switching box and to its zone, or it goes to a switching box and into multiple zones. The other way to do it, and I think only two manufacturers do it this way, is you have a two-pipe mixed flow system from the outdoor unit to a distribution box, or a branch controller, one manufacturer calls it. And you have like in that one pipe, you have both a liquid and a gas together. And this box's job is to separate all of that out. So it's two pipes from here to this box. And then each zone has two pipes home running back to it. The layout of this, the manufacturer equipment is going to dictate that. But your choice as a designer, you may choose one over the other based on the kind of building you have. For example, if I had a school, got this long hallway, and I have all these classrooms off to my left and right as I walk down the hallway, I kind of like this one. It goes down the middle, each zone branches off. I don't want to run piping from every classroom back to that box. It's a lot of extra piping. I got to fit all that in and buy all that copper. However, if my unit is going into a square building and it's going to go right in the middle, and I can branch off into different directions, kind of like in a star, maybe this one on the left is a better choice for me, depending on how my building is laid out. Most people don't consider the piping layout when they design the building, unless it's really space constrained. They just pick the favorite manufacturer that they know how it works, and then they just make the piping work for that project. But the argument here on the left is that in many applications, you have more piping to buy, right? However, you have less brazing connections or flare connections if you're doing it that way. You have more piping connections over here, less piping connections over there. So you're trading off one thing for the other. All right, let's go through this, the heat recovery, heat reclaim operating scenarios. So I got three different scenarios, maybe four, I think, showing you here. In the red dotted line on the left is my outdoor equipment. My 5 indoor units are over here on the right in this case, right? I have a couple condenser coils outside when they're in cooling mode and 5 evaporator coils inside when they're in cooling mode. I have an 8-ton unit with 1, 2, 3, 4, 5, 6, 7, 8 tons in this case, so it matches up evenly. If I'm in cooling mode, these guys are all evaporators. These guys are all condensers. My 2 compressors both run max in this case because I need the full 8 tons. They're sending their hot refrigerant to the condenser coils, right? And then those coils are sending the cooler refrigerant to the indoor units to pick up the heat from your space. That's going back into my compressor. It's like every cooling system we've ever talked about, except that my indoor coils are spread into 5 rooms instead of into 1 room, right? Or into 1 duct, right? Other than that, it works exactly the same. When I switch to heat mode, all heating, in this case, everybody wants heating. Okay, great. It works exactly the same, except for my valves. See these 2 valves, right? These guys are open. These guys are closed. When I go to heating mode, these guys open, these guys close. It's just another way of doing the reversing valves, a little different than those small residential systems you looked at, but same idea. Now hot gas leaves the compressor and does not go to the coil outside to get rejected. Instead, the hot gas goes to the indoor units to send its heat to the inside, thereby sending me cooler refrigerant back where I can pick up heat from the outdoors. It works just like every other heat pump that we've talked about in the past. So hopefully those two make sense. It's just same as every heat pump in cooling and heating mode. I just have a lot of indoor units, right? And this is only 5. I could have 20, 25, 30 of these things on some jobs. Where it gets interesting is when I have opposite needs. This is the cool part. If I was going to do VRF for a building, I would force it into this way. Force it meaning I would lay my building out so it looks like this. So in this case, I have my 8-ton unit. I'm asking for 4 tons of cooling, 1 ton of heating. By the way, a ton is 12,000 BTUs if you want to think of it that way. And then these 2 zones are off. No one needs anything, right? So normally I would run a 4-ton AC to take care of them. And I would run a heating, electric heat, gas heater, whatever for 12,000 BTUs to take care of him. That's not what I'm going to do in this case. I'm going to run my unit in whatever the higher demand is, cooling in this case. So the outdoor unit goes to cooling mode, meaning he's going to send cool refrigerant on this yellow pipe over here to these zones to pick up heat. When I pick up that heat, it's going to go back through the compressor. And instead of going outside to reject the heat, some of it's going to go inside and reject the heat over here. And some of it's going to go outside. So I got 4 tons of cooling. So I have 4 tons of evaporator coil surface, if you will. Somewhere I need 4 tons of condenser coil surface area. 1 ton of condenser coil is going to be over here in this room that wants heat. The other 3 tons goes outside. So I'm going to get a total of 5 tons of heating and cooling capacity by operating my compressor at only 4 tons. And for the heat rejection price outside, fan energy out there and so forth, of only 3 tons. Instead of running a 4-ton cooling and a 1-ton heating. Opposite scenario, I got more heating than cooling in this case. I have 1, 2, 3, 4, 5, 6 tons of heating needed, 2 tons of cooling. The outdoor unit goes into the heating mode, which means the reversing valves flip the other way. In this guy's case, it's going to be picking up 4 tons of heat from outside. It's going to pick up 2 tons of heat from zone number 5, and it's going to run all those guys through the compressor and send it into these 4 zones. So I'm going to get 1, 2, 3, 4, 5, 6, 7, 8 tons of heating and cooling combined capacity for the compressor horsepower operating price of 6 tons, for the heat rejection fan, outdoor fan price of 4 tons. And then if I can get it so there's a certain moment in time where it's exactly even, 2 tons of heating, 2 tons of cooling, this guy doesn't need anything, great. I'm going to operate my compressor at 4 tons. I'm going to shut off all the coils outside, shut off the outside fan, and I'm just going to circulate heat between the zones, the ones that want it and the ones that don't. This doesn't happen very many moments in time, but conceptually, just to give you an idea. Why would I do this? If I go back to that building, right? Here's east, west, north, south, etc. Right? The west zone might need cooling in the afternoon when the sun's beating on it, right? And the interior might need cooling because it always needs cooling. But then the east zone and the north zone might need heating. If I can send the heat from the west zone back over to the guys on the east, why would I not want to do that? Right? Instead of running systems separately for each of them. So in this case, you will intentionally try to mix exposures. Before I said on most zoning systems, whether it's a heat pump or VAV or whatever, I should say VAV's got some exceptions, but VVT, I wouldn't want to mix interior and exterior. I wouldn't want to mix perimeter, east and west, etc. On a heat reclaim, you want to do that on purpose. So it's the opposite zoning mentality. You want to mix east with west. You want to mix north with south. You want to mix interior and exterior. You want to mix it all so you can get as many zones that want heat at the same moment in time as many zones as want cooling. Common applications, a lot of it's been retrofit stuff. And most of it's not this high-rise thing. That's usually ends up being a chiller boiler job, but it could be. But all these other ones, older building retrofits, old schools and old offices, little churches and banks and stuff like that, even some new construction stuff, those are all good applications for this. Historic buildings especially, because you don't have room to put ductwork in most cases, or they won't let you make the room, right? It's easier to get pipes through a wall than ductwork through a wall. And a lot of those buildings didn't have cooling, and now you're trying to add it. And as an option with that, you end up getting heat pump, right? Things to think about when you're pricing this and seeing if it makes sense. Can I even fit ductwork in? Do I already own ductwork? If you already own ductwork, this becomes less exciting. If you don't own any ductwork yet, this becomes very exciting. When I'm comparing the VRF to other systems, I need to add a building automation system to the other systems. I don't need to do that on VRF. It already comes with the building automation system built in. Maybe I need to buy a module that gets it to serve web pages up to my web browser, but that's it. I don't have to buy anything else in terms of field controllers or anything like that. How much space I have, mechanical rooms, things like that. If I'm looking at a VAV rooftop application, I'm buying a VAV rooftop unit, right, which has multiple compressors, variable speed fan, and all that. And each zone gets some kind of VAV box or fan power box, and I have to add my controls. And I need to add all of that up, and then I compare it to VRF, which already has the controls included. In most cases, the VAV rooftop will beat the price of this. Not always, but most cases, depending on whether you can get ductwork in there or not. If you have existing ductwork, then the VAV rooftop almost always wins to replace the existing VAV rooftop. Right? It's easy. When you get to more complicated systems, then that's not necessarily true. And by the way, VRF could beat the rooftop on pricing sometimes, but usually not. If I have more complicated systems, in this case, chiller plant, boiler plant, cooling tower, all those VAV boxes, all those air handlers, and the controls to make all that work versus this prepackaged VRF system, this guy can win a lot of times. You won't do it on every job. Once again, if you, excuse me, if you already own a chiller and a boiler and a piping system and fan coils and air handlers, you're probably just going to keep that. But if you don't have any of that infrastructure, you may choose to do VRF. If it's a high-rise building, skinny, 40 stories, not a lot of roof space, you're probably not going to do this either. I'd rather put one big cooling tower or two cooling towers on a roof than 50 of these heat pumps outside. But if it's a shorter, 2, 3, 4-story building, with more square footage wide instead of high, then it becomes an easier choice to do VRF. From an efficiency standpoint, it's hard to compare these to other things. And by the way, it's always hard to compare different types of products, like I mentioned on module 1. Trying to compare a heat pump to a furnace, to a boiler, to a VRF, to a rooftop, to a chiller, it's hard because they're all doing it a different way. Specifically, one of the big challenges is if you have, this says air-cooled chiller, but water-cooled chillers are the same way. If you look at the efficiencies for air-cooled chillers, they do not include the energy that is required for the fans of the air handlers or for the pumps on the water side. Small split systems include their fans. Rooftops include their fans. VRF includes their fans and any circulation, which in this case is the compressor energy to push refrigerant long distances. So if you want to compare these things, it becomes really challenging. They all use different systems of efficiency ratings, different testing, and some of them do and do not include some of those components. So you cannot directly compare them. The same thing happens on the heating side of the equation with those same pieces of equipment. So we can get ratings for VRF. The ratings from AHRI are very good from comparing manufacturer A to manufacturer B of VRF. They are not good for comparing manufacturer A of VRF to manufacturer C of chiller. Doesn't do a good job of that. You have to energy model for that kind of thing. We've had this rating system for 13 years now for VRF. Before that, it was the Wild West, and everybody just claimed whatever they wanted to claim. Now we have a rating system. It's treated like all the other products. This website, if you've not been there before, is both the best and worst website combined. It's the best because it has all the data on pretty much every manufacturer, pretty much every major type of equipment that you'd want: chiller, boiler, split system, residential, rooftop unit, VRF, etc., water heaters. The bad news is it's a giant mess of data, and you got to learn how to navigate it. So that's the bad side of it. For VRF, there's 4 kinds of systems that are included there. There are the heat pump systems, which means it either heats or cools at any given moment in time, not both simultaneously. And there's heat recovery, which means it can push heat from one zone to the other and run heating and cooling simultaneously. And then for each of those, there's air to air, meaning it takes heat from the air and puts it to the indoors. And there's water to air, which means it takes heat from a water loop and puts it to the indoors, meaning somewhere you have a cooling tower and boiler plant that it attaches to. So those water to air ones would be used in applications where you would have water source heat pumps and you want to further zone them with VRF later on. Or not later on, but downstream. There are a lot of ratings for this. So it has more efficiency numbers than anything else. A, because it's a heat pump, and B, because it also has cooling, and C, because it's simultaneous heating and cooling. I get lots of rating numbers. So you get the full load ER like every piece of equipment gets you. Hey, if I ever have this 95-degree day and every single zone is calling for maximum heating and cooling, what's my EER, right? We said that day hardly ever happens, but we get that number. And if you ever want to convert from EER to COP for any product, you divide it by 3.14. But just remember, it's that COP at whatever instance in time that it was rated, in this case, 95 degrees with all the zones maximum calling. We have IEER, Integrated Energy Efficiency Ratio. This is my part load. We talked about this a little bit on rooftops on Monday, but we basically run the test at 25% loaded, 50% loaded, 75% loaded. No, this is wrong. This is 100%. Yeah. Oh, it says right here. Duh. A is 100%, 75, 50, and 25% loaded. And then we weight them. So we take that average, we take this EER, this little EER right here, and we say that only happens 2% of the year. So we'll kind of count that 2% of the time. And then we're going to rate this guy 62% of the time, 24% of the time, and 12% of the time, and then average all that out to get the IEER. That's for cooling. And then for heating, we'll look at cutoff on the bottom. That says COP, coefficient of performance we have for heating. Coefficient of performance for heat pumps is at 47 degrees. It's kind of an odd number. The reason that is historically the difference between on cooling, difference between 95 and the design indoor temp, which was typically 75, right? Or 80, 67 off into the evaporator coil entering air, that delta T on there. And in this guy, similar type of scenario between my normal indoor temperature was a 20-degree delta T because we were targeting at the time 67 degrees inside. So my 20-degree delta T. So they said, hey, if we run this thing opposite mode in the same 20-degree delta T scenario, how efficient would it be in heating? That's how we end up with 47. Then a few years later, somebody said, yeah, but like, what does that even tell me? 47, like how often am I even running heat? So someone said, you know what, chop 20 degrees off that, and we'll give you a second rating of COP at 17. So you have EER for cooling, IER for cooling, then you have COP 47 and COP 17 for heating efficiency. That's 4 ratings for one system. Then you get a 5th one because it's VRF in this case, and that is simultaneous heating and cooling. So what this does is it says, hey, if we just operate the heating and cooling equally right now, pretend we have this moment in time where everything's operating the same exact quantities, how efficient will we be then, right? So we have that rating. It's in terms of EER, right? But it's going to be a giant number because nothing's getting rejected outside. So it's going to be way up here, right? So how efficient am I in heating? How efficient am I in cooling? As those things track together, it's like I'm shoving heat from one zone to the other. How efficient am I in the middle? And all those rating systems are in here. So we have, I know you guys probably can't see this, but EER, no, dude. EER, IER over here, COP at 47, COP at 17, and then simultaneous in between, right? So this example, the EER is 10.9, the IER part load is 16. That's common for variable speed stuff to have a really good part load efficiency. Heating in this example was 3.2 at 47 degrees, 2.2 COP at 17, and then combined it was 24.7 if I'm running equal parts heating and cooling at that exact same moment. So most of the time I'll be operating somewhere between 10 and 25, right, for my EER. Those are just some examples on there. AHRI certificate, when you print it off, would have all that information. This one's pretty old. I did it back in 2013. So there's even more efficient options now, obviously. How am I doing on slides? I'm running down to my last 5 minutes here. Hang on. Dude, what am I not smart? What's going on? Oh, it's asking if I want to discard my crappy notes. All right, I'm on this one. Oh, we're actually good. Only like 3 more slides of importance here. Okay. This is just showing you an example, and this can be different for every kind of machine. But at the time, this is probably like 6, 7 years ago. At the time, this green line was the minimum legal code efficient chiller. This is the minimum legal air or water cooled version of a chiller, right? And then this red line was a standard VRF system, right? Now you could find a chiller that's way over here, dude. Like we have chillers that are ultra freaky efficient. We'll talk some about those in two modules, but there are chillers that are way up here on the line. But if you're just talking about like basic low cost replacement chillers versus basic entry level VRF, this was the delta in energy savings, right? So that just gives you an idea. When you do compare these, like I said, you have to do an energy model. You can't just say, oh, this one's got this EER and that one got that EER. No, because on VRF, it includes all energy, meaning all fan and distribution energy. On chillers, it does not include pumping distribution energy or fan energy. So it's not a fair comparison. You got to compare it all. This was an example comparing it all. And by the way, if you think I'm like pro VRF and I'm anti-chiller, just so you know, the company I work for, we sell way more chillers than we do VRF. I'm not bashing it. I'm just saying you got to look at everything on your job. So in this case over here, I know you probably can't read the legend, but baby blue is my VRF system, all energy included. The other 5 things are what it takes for me to have my chiller, water-cooled chiller system. So in this case, green is the chiller. If I look at the green and the blue lines, it's like, wow, these are really similar efficiencies. And in fact, this chiller is better than the VRF. I should probably buy a chiller, right? But wait, I got to take the gold color, yellow, and add in the cooling tower energy for that cooling tower fan. Then I got to take the condenser water pump in white and add that on. And then I got to take the chilled water loop pumping system and add that on. Then I got to, in dark blue, take the fan energy for the air handler and add that on. And all of a sudden, VRF could be significantly more efficient than the whole entire chiller plant. Once again, it's not always true because I can get chillers that are way down here for energy, which chops the whole thing off. And I could do a better job on fan energy. Instead of putting a regular air handler in, I could do a VAV air handler. I can cut this fan energy in half. And I can get more efficient pumping systems and put VFDs on the pumps. I can do better than this. Like, obviously, the person that made this chart was a VRF fan. They picked the worst chiller plant they could find, right, and the worst air handlers, and compared it to a regular VRF system. I could get a really good chilled water system and get the line, the total stacked line, to be below this. But many systems are not. They're above this on VRF. You have to do an energy model to compare it. There's at least 5 software tools that do that. These 5 software tools have the ability to model VRF in their energy modeling. There might be others as well, but these are the ones that I'm aware of. And this is pretty much, everybody uses these. A lot of people just use the Carrier and Train software because they have been around forever. HAP and Trace are those 2 software packages. And all of these ones are ones that kind of were birthed out of the Department of Energy modeling tools over time. If you're doing it in a cold climate, there are some things you can do slightly different. As you might guess, I'm going to have some kind of supplemental heat or size my heat pump so ginormous to cover the heat that it's grossly, grossly oversized for cooling in a lot of buildings. I don't usually want to do that. I might, if the building's really tight, built really well, sustainable style building with great windows and air tightness, and I got my heating and cooling loads pretty equalish to each other, right? Then I might be able to just go ahead and do it all with VRF or all with the heat pump in general, right? But if I don't have that, especially on retrofits, my heating BTU needs are more than my cooling. I don't want to size the whole thing for heating because then I'm grossly oversized for cooling. So usually I size for cooling and somebody else helps me out on heating, just like we talked about on the split systems and stuff before. So now I got all these VRF units all over the place, and now I have to add heat to all those rooms as well. 2 ways to do that. One, if it's an existing building with an existing heating system and they got like hot water baseboard going around, just keep the hot water baseboard. Use that as your supplemental heat. Run the heat pump on all the normal hours, and when it gets really cold outside, the boiler will kick on and feed hot water to the baseboard heaters, right? Or radiators or whatever you happen to have already there, right? On your other heating sources. Or if you have electric baseboard, same idea. You run that when the heat pump can't keep up. If you don't have anything out there now and you need to add heating to all those zones, that becomes very costly, right? So in those cases, this is a trick you might want to consider. I don't remember where I got this picture from, but the first place I saw this was one of the mechanical contractors in Wisconsin did this at their own office building. And I just thought it was at first I was like baffled, like, what the hell are you doing? And then I was like, this is actually quite brilliant. So instead of putting heaters out in all their zones, what they did is they put their heat pump inside the building. Instead of rejecting heat to the outdoors or getting it from the outdoors, they get it from a room and reject the heat to the room or pull it from outdoors. Now, obviously, you can't do that indefinitely because the room gets hotter and hotter or colder and colder. So the room has to be connected to the outdoors. So they have this room sitting on the outside of their building. They have these louvers on the wall, and then the top of the heat pump, they duct to the outside. Not every heat pump can do this, but some models can be ducted a short distance. So they suck air in from outside, run it through their heat pump, and send it outside. So it's basically like the heat pumps outside, right? The heat pumps outside, but just sucking from this wall. Then what they do is when it gets colder and colder outside, they can modulate these dampers a little bit more down, so it sucks less air in, and instead uses air from the room a little bit more. But more importantly, that's a minor thing, but more importantly, they can install heaters in that room, either electric resistance heaters or even gas-fired heaters in that room. And now this heat pump is pulling its heat from that room. And instead of being 0 degrees outside, it's 30 degrees in the room because that supplemental heater is adding heat to that room. It sounds kind of hokey. And you're like, dude, why am I going to heat this room instead of just heating the zones I care about? Well, the reason is now I have to pull one electrical feed or one gas line to heat that room versus pulling electrical feed to 33 zones, right? So it's a lot less on the installation cost. Not a great idea for every job, but there are jobs where this might help you out. All right. And then the last thing on here was a couple case studies. I'm going to leave them on there so you guys have those notes from a couple different buildings. But it doesn't really directly apply to our moment right now. Did I miss any questions? Let's see. I think I got all questions answered at the moment. If there's anything else we want to talk about, throw it on here. Our next module will be Monday afternoon, right? Because today's Friday. Monday afternoon. And we'll go through hydronic boiler systems, hot water systems, a little bit of steam also, but mainly hot water hydronic systems. And we'll talk about how we can make those into heat pumps. Either heat pumps themselves for the boiler, make a heat pump boiler, or supplement the boiler with a heat pump. We'll talk about both kinds of scenarios. But first, we'll go through how a basic hydronic system works so you know what the hell you got when you see one of these out there. More questions? Anybody? All right, cool. I'll stick on for like another minute or two in case another question pops up. But otherwise, I thank you guys, and I'll see you guys on Monday.